Okay, awesome. Thank you so much for the invitation and the introduction, Jason, and thank you also for Alyssa Johnson and everyone else. Yeah, and thank you all. I know it takes a lot of work to organize a US Clever webinar series. I did it in the past, so thank you all for coming today. And I want to also take time to thank all my research collaborators. A lot of that work was done at UC Irvine in Colombia, and then I kept doing it in Switzerland. And Jason, let's see. So Jason sent me two questions, which I summarize here. He said they were part of the overarching questions you all were investigating. And these were how to balance high performance AI with climate process understanding for climate prediction, and I'm guessing projection purposes, and what are best practices for conducting machine learning studies in climate prediction. And these two questions, I think, resonate quite a bit with the overall idea of physics-guided machine learning, which can be defined in many ways. It's a pretty recent field, but a possible definition is that its goal is to restrict the output of machine learning algorithms. And here I'm going to use machine learning in the broadest sense. So think of any type of data-driven algorithm, from your simplest multiple linear regression to a very representative neural network that can learn nonlinearities, connectivities. And so the idea is that among all the possible solutions that these algorithms can produce, you're going to add physical structure to restrict the solution space to solutions that are physically plausible. And I think an example that tends to be quite intuitive for atmospheric scientists is relative humidity. And as it's defined between as a ratio between the partial pressure of water vapor and its saturation value, its physically plausible range is between 0 and 1. By definition, it's strictly positive. And so you would never want to predict a negative quantity. And an example of using that very simple physical knowledge would be to impose what we call a hard constraint. So you wouldn't waste any optimization trying to find negative solution. And for example, in a neural network, which are more advanced machine learning architectures, relying on activation functions, these are nonlinear functions that you can compose to get you a solution. You would use an activation function that only output positive number because you know relative humidity is going to be positive. In contrast, relative humidity is generally above 1, but it's not always above 1 because you can have supersaturation, especially at very fine spatiotemporal scales. And so in that case, we would maybe impose a soft constraint. So we would encourage the solution to not be too much above 1, but we would tolerate some of these numbers larger than 1, and that can be achieved in many ways. If you're interested in deep learning, for example, you could minimize a rectified linear unit of RH minus 1 to kind of push it towards 1. And this is one particular example, a pretty simple example, but more generally, we can encode much more sophisticated physical knowledge into data-driven machine learning algorithm. So much that at this point, it has become a field of its own, a subfield of knowledge-guided machine learning. And I like to think of it in terms of this two-way interaction between the knowledge that we have, physical knowledge, and data, as well as data-driven algorithms. And physics-guided machine learning is really going from left to right to use that physical knowledge that we have to guide machine learning algorithms and make the most out of the data we have. And it's typically contrasted with data-driven discovery, which I'll touch a little bit upon at the end of the seminar. But what I'm going to show you now is 3 examples of physics-guided machine learning applied to climate, to weather and climate problems, where we've successfully used knowledge that we have about atmospheric physics to make the solution, the predictions of the algorithms more consistent with the knowledge. And the first problem I'm going to tackle, and because we only have 20 minutes, I don't have time to give you the full context, But here it's going to be in a climate parameterization context. So parameterization is these modules that we use in climate models to represent uncertain processes, in particular those below the grid scale and what we can resolve. And there's a source of large uncertainties in our climate projection. Machine learning allows us to design more faithful parameterization using the data that we have, whether it's from high fidelity simulations or observations. But the problem when we do that, and we just take off-the-shelf machine learning algorithms such as neural networks, is that they're going to violate conservation laws by taking shortcuts. So if I take a histogram of the residual from conservation laws, on the top I'm showing the residual from the mass conservation, and at the bottom from the moist enthalpy. You can think of it as a convenient measure of energy for atmosphere for what I'm doing here, which is subgrid parameterization of thermodynamic processes. If the neural network perfectly followed the conservation laws, you would expect the residuals to be 0. But in practice, if I optimize these algorithms and run a batch of different samples, different atmospheric columns through the algorithms, I get these really large residuals. And here I'm expressing them in unit watt square per meter 4. And so it's typically much larger. Just in a single time step, it's going to be much larger than the forcing we typically impose when we run in climate projections. And so that's a real problem. If you present that to climate scientists, climate modelers, they're not going to be happy justifyingly. And so in that case, this is a constraint we really care about. We don't want spurious mass, spurious energy to appear in every time step of our climate simulations. And so what people typically do is to introduce the soft constraints, similar to the soft constraint of relative humidity larger than 1 that I mentioned earlier. And in that case, one can introduce a penalty for violating conservation. So in the optimization objective, such as the loss function, you would add, in addition to mean squared error, what you're trying to optimize, a part that's going to encourage a neural network to follow the physical law. But as I'm going to show you, if you do that, you're going to end up with a trade-off between physical constraints and performance. So on the y-axis, I'm going to show you the loss of the neural network. So the lower you go, the better. So if I take a neural network, it typically beats a linear regression. This is what justifies deep learning. We strictly, statistically significantly better than linear models. And so this justifies considering neural networks. But as I crank up the weight of the physical constraints here, I'm going to have a compromise between these residuals that I'm trying to minimize and the error. So I'm going to show it to you now. If the more I crank up this weight, the more closely I'm going to follow these conservation laws, but the worse the performance is going to get. So I have this strict trade-off if I just add the physical laws to my optimization objective. And so this motivated us to be more creative about how we enforce these conservation laws. And we designed a technique to enforce it within machine precision for this particular problem, but I'm going to show we made it much more general. So here you can consider any mathematical mapping, so any regression where you're going to try to predict outputs as a function of inputs. But instead of outputting all of your outputs, if you have p outputs and n constraint, you're going to output p minus n direct outputs. And then you're going to calculate the rest of your outputs as to exactly follow your constraints. So here we assume we know our constraints, that they can be written in terms of differentiable algorithms. You're going to put them right here, and then you can calculate the rest of the output using these constraints, in our case, the conservation laws that we have. And the trick is to all do it inside the neural network. So using a differentiable programming language, it can be TensorFlow, PyTorch, Keras, JAX. The general idea is quite general. Sorry, the general idea works across programming languages. And then we feed the whole output vector to the loss function, and then we optimize it. And because this is all done inside the neural network, we still make predictions that are encouraged to be accurate. So, going back to the first question Jason asked, we're still going for performance because we optimize the entire thing, but we build the algorithm so as to exactly follow the conservation laws. And so in that case, there's barely any compromise. There's a little bit because we have a lot of inputs and outputs, but we managed to get a performance that's competitive with a version that's completely unconstrained. And then our physical constraints residuals are 0 to within machine precision. And this encouraged us to go towards more operational case. So now I'm going to present a numerical weather prediction case where it's Mutual Swiss who approached me because they were interested in this framework and they had an excellent student working on it. And they thought, you made it work to enforce conservation laws. We have this problem where we violate state equations when we post-process weather for operational predictions. Could we use a similar technique? And so here it's a Swiss example where the goal is to post-process surface variables, so surface temperature and surface humidity using neural network. And so for those of you who aren't familiar, post-processing are these algorithms that take the outputs of numerical weather prediction models and then use statistical relationship to make these outputs as close to observations as possible. So it's a very operational problem because when you open your phone to get your forecast, you're getting the outputs of the post-processing models that learn very fine relationship. For example, you're on top or at the bottom of a hill, which is going to change the temperature by a couple of degrees or much more if you're on top of a Swiss mountain. And typically, this is done purely statistically. And so the question is, can we use the same framework to, instead of enforcing conservation laws, enforcing Clause's Clapeyron and the ideal gas law? And so to enforce constraints, so here you're trying to predict temperature, dew point temperature, pressure, relative humidity, and mixing ratio near the surface. Instead of directly predicting it using the neural network, you're going to repeat the same procedure. You're going to have, if you have the ideal gas law and an integral for Clause's Clapeyron equation, you have two equations, and you have 5 variables to predict. So you only predict 3 variables, and then you calculate the 2 remaining ones so as to exactly follow the physical equations. And then you optimize the entire network, just like we've seen before. And if you look at how much the output violates the thermodynamic state equations, for no constraints, you get large residual. For loss constraint, so the soft constraints, you get some residual. And then if you do it that way, your residual is 0 to within machine precision. And in that case, because it's a very low dimensional problem, because we've only post-processed 5 variables, you actually improve the performance. So this is the kind of problem that mathematicians and physicists love when they design these kind of architectures, because it's a win-win-win. You have more physically consistent solutions and you gain in performance. And my experience in climate science is that this is only true for low dimensional problems. For high dimensional problems, there's a lot more degrees of freedom and you don't always get all these wins together. And then there are other advantages of designing, putting some physical knowledge in. It gives you really good prior, for example, if you think in Bayesian terms. So you need a lot less data because you've already fixed some degrees of freedom. You only have 3 degrees of freedom less. You need a lot less data to train the neural network. So if you reduce the fraction of the training data, what you find is that the architecture constraint performance is going to get better and better relative to the unconstrained neural network. And you can train these physically constrained models with a lot less samples, which makes sense if you've used knowledge that strictly holds for the data you're considering. So I've shown you that we can enforce conservation law, state equations. More generally, this kind of framework allows you to enforce any constraint that you have. It can be physical, chemical, biogeochemical, as long as you can encode it in terms of a differentiable algorithm and that it's verified in your data. That's sometimes decently restrictive, and there's one thing it doesn't guarantee, and I'm keeping an eye on the time, but I'm guessing since we started a little bit late, maybe I can go up to 25. Is that fine?
Yeah, that's fine. Yeah, absolutely. Yep, keep going.
Okay, perfect. So what we've found is that even when we physically constrain, so going back to the parameterization example, even when we physically constrain the output, it doesn't necessarily guarantee generalization, especially in out-of-distribution scenario. So a typical one in climate studies is climate change, where the temperature conditions are going to change a lot. And so you're going to be exposed, these data-driven algorithms are typically exposed to inputs that were not trained for. And so we took these physically constrained architecture and we tried them again in a climate simulation where the surface was warmed by 4 Kelvin, and we found that they failed. And then we were curious, so we broke the model even more by designing a generalization experiment that was quite drastic, 8 Kelvin, to just try to see how much the model breaks. So these are just representative pictures. Is not actually the how the simulations we run, but we've tried it in many different settings. So we've tried it in aquaplanets, in real geography scenarios, and we've tried it in several different climate models. We train and validate data-driven models in cold simulation and test them on simulations that are 8 Kelvin warmer. And this is the typical prediction we faced with. Our parameterization have to predict the full vertical profile of subgrid moistening and heating. We only interested in data-driven algorithms such as neural networks that work well in the climate that we're trained in. And then we warm the climate by 8 Kelvin. And in that case, and that's a pretty standard neural network, it broke really, really dramatically the first time we tried it. And then we kept getting this failure mode. When we increase the surface by 8 Kelvin, here we're making errors that are 5 to 10 times larger. So I personally really like these problems because then you can clearly see which solutions work and which solutions don't. And the solution that worked were based on simple data analysis. So if we look at the conditions these data-driven algorithms are exposed to, like specific humidity, because of Clapeyron and its consequences, the amount of water vapor the air can hold increases near exponentially as the temperature warms. So if we look at the histogram in the warm climate, it has a significantly longer tail than in the cold climate. But we know Clausius-Clapeyron relation, the Clausius-Clapeyron equation, so we can form relative humidity. And in that case, the histograms are much more similar. So we've transformed what is an extrapolation problem into something that's much closer to an interpolation. And if I take the same type of prediction and I rescale the input, the generalization improves already quite a bit. And then we took this result and we transformed it into a much more general framework. So what we saw, and here I'm representing the mapping mathematically, but I'll show you the corresponding distribution quicker. We're trying to predict the subgrid response of clouds, turbulent convection, given climate condition. And if we learn this mapping during just the raw data that we train with, we've seen that the mapping is not the same in the cold and the warm climate, which explains the failure mode. And that's because the distribution of the inputs are not the same, specific humidity, temperature, surface fluxes, and the outputs are not the same as well. But now if you use our physical knowledge to transform these inputs and the output variables to get distribution that are much closer, they don't need to match exactly, but at least we're in a regime where data-driven algorithms do well. It may be out of sample, but it's not completely out of distribution. We generalize much better. And this is true for an aquaplanet, that's what I just showed you, but if we repeat it for a real geography experiments, so simulations with realistic continents, it works really well for variables like the near surface subgrid heatings. It works on the whole profile. I'm just showing you typical variables we tend to care about for subgrid parameterization. So this is the amount of heating near the surface from convection and clouds. With that, the physical transformation, I'm showing you the error, the coefficient of determination. 1 is for perfect prediction, 0, the error is order 1 standard deviation. It can go all the way to minus infinity because it's a coefficient of determination, not correlation. So here we see how much the neural network struggles to generalize in the tropics. And if we use the physical transformation, It doesn't solve everything, but it gives you a really good prediction. And that's even more true for atmospheric centric variables. I want to briefly comment on the two-way interaction between knowledge and data. I want to show you, I work a lot on the other arrow too. And I'll go back to Jason's question at the beginning. I think it also mentioned these two-way interactions. Once you've done that work, and that's arguably more, we framed it more as a machine learning and a mathematical problem than a climate problem, then you can use that setup to learn something about the underlying physics. And so here I'm using an interpretability technique to visualize the mapping that the neural network learned in the climate invariant case. So that's the case where I physically transform the data on the left and I generalize to warmer climate versus the raw data. And I'll put the reference to the paper, but what we see here, if you just look at this matrix, that gives you how the outputs on the y-axis respond to the input of the x-axis, you see that this one is much closer to the diagonal than the climate invariant one is much more diagonal than the raw data one. And what that tells us is that the relationship we learn is much more local in the vertical, because relative humidity, for example, at 500 hectopascal is going to mostly act on subgrade moistening, heating and moistening at 500 hectopascal. And that's because our transformed variable, buoyancy, relative humidity, are much more directly connected to the outputs we care about. So just taking a couple of steps back and coming back to the initial question, I hope I convinced you that by using relatively simple, well-established physical knowledge, we can restrict the outputs or change the behavior of neural networks so that they don't violate conservation laws or state equations, which are some of the relationships in atmospheric physics we can write and encode best. And in the case of relationships that are less easy to directly write down, I hope I convinced you that by physically transforming variables, you can help neural networks generalize across climate when they couldn't before. And to go back to the question Jason sent me before the meeting, how to balance high-performance AI with climate process understanding and climate prediction. I hope I convinced you that you can use climate process understanding to improve performance if we define performance, and that goes to the second question, not just from a pure error minimization perspective, but also from a more holistic perspective, using metrics we would care about for climate model evaluation. And with that, I'm going to thank you to not go over time. So if you're curious, all of this is published in 3 papers, so, well, and more preprints. But the constraints one, it's a PRL paper in 2021. The Meteo Swiss one is in AMS-AIS, and the climate invariant one, after 3-4 years, it's in Science Advances, but you can see all the preprints that evolved. So there's a lot of resources online if you care about the quantitative details, and I'm happy to provide more in our discussions.
We'll just go to Michelle first.
This was very thought-provoking, very nice talk. I didn't understand all the details, but I got the gist of it. I'm going to ask a little bit of a provocative question, which is, you've, I'm sure, heard of Google GraphCast and how
Yes.
that is competitive with NWP pure methods.
Yeah, we work on it.
Do you think that is mostly physically consistent? And if not, does it matter? It's a little bit of a provocative question.
And there's so many ways to answer it. So some people will tell you that for numerical weather prediction, especially for short time scales, we don't care as much about interpretability and physical consistency as for longer time scales. Obviously, you saw what we're doing with post-processing, so I don't fully agree with that statement. But I do think GraphCast is really impressive at minimizing the root mean squared error for the deterministic prediction. And that will naturally force you to follow some physical laws implicitly, or at least be close to them through the data. Now, it's taking a risk. It's giving a lot of degrees of freedom. And this, if we just stay in Google world, they have two more recent work that address some of that physical inconsistency. So for example, they designed the neural GCM, where for the dynamical core is based on the fundamental primitive equations, and they learn some of the physics. And so that's going to be much more physically based and naturally have a more consistent spectrum, etc., albeit maybe with a slight trade-off in performance. And also the teams that designed GraphCast came up with GenCast just last month. And that's making it stochastic rather than deterministic. And they get more physically consistent structure that way because they don't just minimize the error, they also optimize for the spread. And then they get more realistic, for example, cases of extremes like tropical cyclones. That was a bit of a long-winded answer, but I think we can talk about it for a long time. I think GraphCast will be taking shortcuts by design, but I think for some medium-range forecasting applications, that's not necessarily a big deal, and you can always add back those physical constraints in the post-processing algorithm.
Thank you. That was wonderful.
All right, so Dan next. So Dan, go ahead.
Hi, Tom. Thanks for a nice talk. I wondered if you could talk about differentiability. Is this program kind of restricted right now to models that have adjoints or maybe emulators built on them, or how can we go about doing that?
So I think as long as you use a differentiable language, you're fine. And so, for example, for example, as long as you code things mostly from scratch, which, for parametrizations, you can, and you write it in TensorFlow, JAX, something you can differentiate through, this works. The only time it doesn't work is, for example, if you're going to try to interact with a dynamical core written in Fortran, for example, where Fortran is typically non-differentiable. So there's a lot of efforts right now by various really big centers and groups to rewrite some of the Fortran code in Python and JAX, etc., so that it can be differentiable. But so it's only whenever you interact with code that's non-differentiable that you hit walls. But for all the examples I presented, like a post-processing algorithm or parametrization, you can just write the whole thing in whatever language you want. So then it's not very limiting. I don't know if I answered your question.
Yeah, I guess I was thinking of it from the context of these, larger Fortran-based models, and if the path forward there is, converting those to other languages, it sounds like, the examples you gave, I guess, were more closed parameterizations where you could write things. I was just wondering if there was some other quick fix that might help with the problem.
Well, I think, for example, a lot of the LEAP Center, that's a big NSF center at Columbia, many other universities, they're rewriting some of the American models in Python here in Switzerland at ETH. They're rewriting a lot of Icon in Python. So I think if you want to make the full climate model differentiable, there's no way around it. Now, there's some interesting work that tells you how to emulate and learn, optimize this parametrization with the code, even in non-differentiable case, but I can send that to you. That's more experimental. So people are even, if you don't have such a big team, people are thinking of hacks to get around it, but that would be a much longer conversation.
Thank you.
Okay, Matt is next.
Yeah, hi. Thanks, Tom, for a very, very nice talk. Obviously, this is an important direction as we get into these longer timescales, and kind of along those lines. I'm curious what you would say. This is more in the nature of help for us in terms of this white paper, of how one would go about doing the kind of things you're outlining here when you want to also include the ocean. So when you talk about energy conservation, for example, you're really taking it from the atmospheric perspective and not from the entire climate system. which is okay for weather. And of course, most of this work has been aimed somewhat more along those lines. But on a climate time scale, where we don't maybe even have the observations to entirely constrain the energy budget as it is, how does one go about doing that? And then, of course, in addition, when you're also worried about the fact that even the entire climate system itself doesn't have kind of constant energy distributions or potentially even input, although that's secondary. How does one deal with that in this framework as well?
Yeah, I don't think there's a single possible solution. I think that's a huge research topic that a lot of people are thinking about. As you noticed, I'm not running any coupled simulation there, so that's why I don't run into the problem you're mentioning. It really depends on your modeling philosophy. If you believe, for example, that you want to keep the primitive equations, and then I think the hybrid, the middle of the road philosophy is to keep the primitive equation for the scales you understand, and then for the scales you don't understand, so processes that are complex and you want to use any kind of data, remote sensing, or observations, etc. Then you design data-driven models, but for the individual processes. So that's a philosophy I think that's more compatible with Earth system modeling. For the weather timescales, you can emulate the whole thing and you can validate it, but for climate we cannot. There's a lot of we can't validate the entire. We don't even have we don't have future data, right? So we can't validate the entire output. We can validate individual processes. So I like this middle of the road philosophy where you keep conservative equations for what you know. So you have an overarching structure that will conserve heat at the global scale, momentum at the global scale, etc. And then you just have data-driven processes. And then if you do it that way, then you only really have to conserve the appropriate variables in these individual processes. So all of a sudden, it becomes a lot more tractable. So for example, if I take an ocean example, and I think, Lausanne's group and others, they have a lot of work on it, you can just aim at conserving subgrid momentum or the appropriate equations, the appropriate momentum equation if you're parameterizing subgrid momentum fluxes. I'm sorry, I don't have a single answer for that, but.
So doesn't that run us into the same problem we have with models with the kind of parameterizations we do, where, and Laura's is a really good case because this is what has really struck me when I've heard her give presentations on her work. One of the big problems in tuning models is every individual parameterization is at some level the best. And if you take the best parameterizations and drop it into the climate model framework, you do not get the best result. Mm-hmm. And I worry that people in the machine learning community are going down exactly that same road. You can come up with individual parameterizations along the lines you're talking about, but what do you do when you combine them all in? How do you ensure that the sum total of your model now still, say, conserves energy and momentum, which you, in your parameterizations, if they're not interacting with the rest of the model properly, you could potentially find that's still not the case.
So there's two aspects in your question, and I want to separate performance from energy conservation, because you can think about the mapping and make sure that however you're formulating the model, it's conservative. It doesn't mean the parameterization is good, right? But you can be intentional about making it conserve the right quantities. And that's different from the other point you were making about model calibration. And as groups have made progress from experimental prototypes to plugging them back in climate models, I think the general consensus is like that. The same as for every other parameterization, you have to retune the model, because even if you did make your parameterization better, more consistent with observations, there were some compensating biases, so you're going to have to recalibrate it. Now, the nice thing is that machine learning models can be more easily calibrated if they're well designed than traditional parameterization, especially if you're in the limit where everything is differentiable. Then you can be very, very intelligent about how you calibrate each parameter. For example, a lot of the Klima framework, like Bushnatter, etc., is very intentional about that. But that's kind of in the luxurious case where everything is differentiable. I think it's much more delicate when you're interacting between data-driven components and the Fortran core. And my experience with that is mixed. It's really a research topic, and that's what I was telling Dan. I think the research is still ongoing about how to best calibrate these parameterizations with a Fortran base code, like Dynamical Core, for example.
Okay. I don't see anyone else's hand up, but I'm going to ask a question. So I was a little bit interested in the sort of the last part of the talk where you're talking about, using the physics to take from one climate to another and making sure that we're still preserving everything again. And that got me thinking about one of the other issues. I mean, not just with machine learning parts, but also with numerical weather in some aspects, sometimes, not really, but with machine learning for sure, is extreme weather prediction. So trying to predict extremes, whether it be temperature or precipitation or wind, or perhaps an ocean model predicting, extremes in some of those variables. And so I'm wondering, is there an analog that could be used in sort of either in the maybe in the subseasonal or season to seasonal realm, based on what you did in the climate scenarios, the two different climate scenarios, to sort of help to bridge that problem? Because of course the problem, of course, is that you can train our models all you want, but by definition the extreme weather is rare, right? We can have examples, but they're very rare. So the model will not tend to predict them or underpredict the amplitude or magnitude.
Sorry.
So is there an analog that we could use in what you did with the climate, with those sort of transforming between
we're thinking a lot about it.
to do with extremes, but on the weather scale, like a seasonal, even synoptic, but let's say sub-seasonal scale.
That's a really good question, and there's many different opinions, but it's certainly a topic that's being investigated. I'm also interested in it. I think a lot of papers, so that's not analogous to what I did, but a lot of papers will argue that maybe you can pre-train on really, really large data that's not exactly the same, like CMAP6. And then fine-tuning on then, I don't know, your problem of interest. I don't know if it's S2S. And that will mean you have seen extremes during the training. And then if you're smart about the loss function, you then do better through what you've already learned. And philosophically, that's really the data heavy approach. And when you hear about foundation models that are trained on very, very large databases for different purposes, that's an approach a lot of the field is taking. I guess because I'm more of a physicist, I like to think about it similarly to what I presented today in terms of, do we have constraints? Do we know something about the tail of the distribution that would allow us to, even without having seen too many extreme samples, not give inconsistent answers in terms of extreme? And that's some of the work we've started to do here, thinking a lot about how to combine, for example, machine learning with extreme value theory that gives you some predictions about the tail. But that's a lot more experimental. So that would be the analogous approach. And then bonus if you have robust knowledge of extremes. Sometimes, you have physical knowledge of these extremes and you could very much transform your data so that what is an extreme becomes not an extreme in the new phase space you're learning in. So there's a lot of fun experimental work to be done. And then the more brute force approach is just to pre-train on very, very, very large data sets that have synthetic extremes.
Okay. We're going to go one more question here, and I think Hey Long.
Yeah.
Ask?
Thank
Go
you.
ahead.
Can you hear me?
Yeah.
Cool. Yeah, thank you, Tom, for the very nice presentation. I wonder about your opinion or perspective on using machine learning to replace physical processes in weather or climate models. For example, we use there are lots of uncertainties to predict clouds, cloud properties, cloud drop number, all those properties. But offline machine learning, we can based on lots of data to use aerosols, meteorology to train a machine learning algorithm to predict. It's doing very well. However, use the well-trained machine learning algorithm to predict one snapshot or short time cloud property based on the same input is very challenging. So do you have any comment on this?
Yeah, I don't want to give a single answer like, oh, you should replace all your physical parametrizations with machine learning if they perform well. I think it really depends on the situation. You can make a parameterization a lot less expensive by parameterizing it with machine learning. So if we take the example of radiation, which historically was one of the first examples where researchers at ECMWF in the 90s took machine learning and emulated radiative transfer, not perfectly, but well enough for meteorological purposes at the time in that model. Then you can cut the cost, and then you can call radiation at every time step instead of having to call it at irregular intervals. In that case, the added value is clear because they were trying to accelerate the models. But in other cases, you may not, and I think the climate timescales is a good example. You don't want to put an algorithm that you don't fully understand in your model because there's so many other components you don't understand, and uncertainty is part of what you're trying to predict. So then maybe what I like to think about is using machine learning as a way to generate hypotheses. So a lot of our parameterizations are imperfect, but we don't exactly know why, but we have really good data. And what we can do is create a machine learning parameterizations and try to distill its added value. So why did it beat the parameterization I had before? And then the hard work that, I've done it in collaborations with other researchers from GLR in the case of cloud fraction, but I think there's a lot more work to be done is, once you have that added value, you can distill it back to a simple equation. So you can do the really, really hard work to find a sparse model that has the same added value as your machine learning algorithm. But now that it's sparse, you can see the equation, you can interpret it, it's asymptotic behavior, you know how it behaves, you can make it conservative if you want. And if you do that second part of the work, which is not always possible depending on the problem, then you've learned something scientifically and your added value and your hypothesis are very transparent, which often you care about. And for example, if you generalize poorly, if I have it in equation form, I can tell you why. If I have a giant neural network, it's going to take a lot longer to analyze. So my answer is, again, it really depends on your goal, but I think there's a lot to be done, especially because we have more and more and better data. So it's about using it to generate scientific hypotheses and improve our models if we can.
Great. All right. Thank you very much.